our first speaker is Dr. Priyanka Gulia from IIT Delhi. She's an assistant professor in the Department of Computer Science and Engineering. Prior to that, she was a faculty member at the CISP Helmholtz Center for Information Security. She is focusing on artificial intelligence and automated reasoning. Her research interests are on those fields. Okay, let's welcome the speaker and over to you.
Thank you. Thank you, Day-3, and thank you for having me here. Is it working? Mic is working? Can you hear me at the back? No?
No, please.
Now? Good. So today the talk is going to be about using AI. AI everybody knows. And AR for automated synthesis. How many of you know about AR? Augmented reality. Augmented reality. Anybody else? Automated reasoning from a professor, right? So we should ignore it. So okay. So that's the audience I'm talking to who does not know about AR. So by the end, my goal is that you should know about AR and I will be happy. Everything else is you can forget, but not AR. So AR means automated reasoning. Okay, so let's get started. You know, in 1940s, the IBM president then, Thomas Watson, said there is a room of about 5 computers. And today, everybody knows that we are living in a world surrounded by complex computing systems. They are performing surgeries for us, they are driving themselves while we sit back and relax. They are assisting with day-to-day life, and we are relying on these complex computing systems to make decisions for us, whether or not to give you admission for PhD program. That is by an AI, right? So, all of these systems are part of our day-to-day life. So what do we want from these systems? We want to trust these systems, right? We want to trust that whatever the decision they are making are going to be accurate and reliable in all possible scenarios they are going to face. And that is what we mean by trustworthy system. Can you tell me what kind of strategies come to your mind when I say trustworthiness? How are you going to achieve that? Privacy. But I'm saying that we want to achieve the trust. Correctness. What else? Reliability. How are you going to achieve that reliability and correctness? Suppose you have a system with you, right? And I claim that this is correct. How are you going to check that? Sorry? You have to speak a little bit louder. Analysis. Okay. Or anything else? Authentication. What are you authenticating?
Information retrievers matching with the
AI to bola hi nahi na. I did not say AI so far. I'm saying you have a system.
performance and results.
I'm saying that this is the system. Suppose the system is to schedule our talks, right? It took our timing constraints and give us a schedule. I'm saying that no two schedules are consecutive. Maybe our organizer wanted a coffee break in between. So I'm claiming that the scheduler is not going to give you a schedule in which 2 talks are consecutive. How are you going to trust that? Very easy, right? Verification. Certification. How many of you know about verification? You know about verification. What is it? Certification / verification I'm going to use interchangeably, which is not the case in ideal scenario, but I'm talking in a weak representation, is that whatever the system you have in your hand, it is doing what it was intended to do. Right? Have we made what we were trying to make? That is what the certification is. Here, when I say system, it can be hardware, software, AI models, whatever it is. And we want to see whether this system is reliable. It satisfies certain properties. Properties can be reliability, robustness, fairness, according to your application. So we have some modules, we have some systems, and we want to check whether the system satisfies those properties or not. How can we check? We can ask the question, is it always the case that the system satisfies the property? Or contrapositively, I not satisfy the property. And if I get an input for which the system do not satisfy the property, I have a counter example saying that here is a proof. For this example, So this particular question can be answered by a lot of progress in the field called Boolean satisfiability, SAT solving, SMT solving. What it takes a formula as an input and ask the question, is there exists a solution? What do you mean by that? As I said, it's a Boolean case. Basically, all variables can take 0, 1 value. So give me an assignment, 0, 1 value to the variables such that the formula becomes 1. Just to ensure that everybody is on the same page. Suppose my formula is a toy formula, x1 or x2 or x3. These three variables can take only 0, 1. That the domain of these variables are Boolean. So under this assignment, 1, 1, 0. The formula is 1 or 0, which is 1. So this is a satisfying assignment. So you can actually represent this system, abstract out as a system of input I and output O. You can abstract out the properties as over input I and output O, convert into a formula, pass it to these solvers and get whether it is always the case that the system satisfies the property or not. This is specifically with respect to the Boolean, but we have solvers satisfiability modulo theories in which you can represent this formula as linear integer arithmetic, linear real arithmetic, strings and so on and so forth. Just to ensure that everybody is on the same page, I'm showing an example with respect to the Boolean case. Okay, so one way to achieve trust is this Boolean satisfiability via certification using solvers and so on, right? Another way could be designing a system which has these guarantees inbuilt in it, right? That is what we call as correct by construction. When we design, we have this verification repair loop inside it, such that when we say that, oh, I have this system for you, you can have a certificate attached to it saying that it is always going to satisfy the property. That is what we call as correct by construction paradigm. So what it takes your specification requirement, whatever the language you are comfortable with, pass it on to some system, and that system will give you probably correct system. It has correctness guarantees. And how we are going to do this, that's what we are going to discuss today. The synthesizer we are going to open up. So, this is the focus of this today's talk. When I say specification, it is going to be logical relation. Later in the talk, towards the end, we are going to uplift it towards the programs and functions. But just to ensure that everybody is on the same page, currently, until unless I explicitly mention, the specification is a logical relation. There is something going on, and finally we'll get the probably correct system, and there's something going on, I'm going to open up in today's talk. Okay? Of course, it is a sequence of work done with my advisors and now my students, and we are going to discuss this today. Again, I'm going to repeat the problem statement. So what we have inputs, many inputs, and many inputs. We have outputs, and many outputs. And we have some specification over this input and output. What we want to fill this black box, purple box. What does it take? It takes this input, does some calculation, outputs the output y. Such that this x and y, when you put together into the specification, they must satisfy the specification. So this black box can be a program, can be circuits, and can be functions. So notice here, each output is a function of all the inputs, x1 to xn. Right? So I can fill this black box with whatever I want. Program, circuits, functions. The goal is that x and y together should satisfy the specification. Can you tell me what will be the functions with respect to this? Let's assume that it's a 1 bit. So x is equal to y1 times y2. And I tell you that y1 and y2 cannot be the trivial ones. That's the specification. X is equals to y1 times y2, and y1 and y2 cannot be the trivial one. What do you want? You want to represent y in terms of x, such that x and y together should satisfy this equation. Any idea? I know it's after lunch, but I'm not going to move ahead until I needs to tell me the answer. We can wait until for 20 minutes or more and then we can go. You have to tell me the answer. At the back. X is equals to y1 times y2.
What is that product mod n and a product?
This is an n-bit vectors actually, so the multiplication with respect to
So
that.
if there's any overflow,
Simple case, no overflow, nothing at this moment. It can be in real scenario, but let's just see. Isn't y1 and y2 are the factors of x? Non-trivial factors. If we had a factorization algorithm that takes x as an input and gives you two non-trivial factors, that is going to satisfy this equation. Yes or no? So that you wanted to come up automatically. That's what you wanted to synthesize. So now you see, so specification looks like this. What you want to synthesize y in terms of x. So your program will take only x as an input and will return y1 and y2, which will be non-trivial factors of x. So now with x and y, if you put together into the specification, they are going to satisfy the specification, right?
y1 and y2 here are the binary.
So m is basically the summation of at y and y2, the size of y1. So okay. So this is the problem. Again, because I am a formal method person, I have to give you some notations. Otherwise, I will not be happy. So same problem with different notation. See, this is nothing. It's what it says is that the specification is given, right? Over input x, x can be x1 to xn. Output y, y can be y1 to yn. What I want to synthesize each y by I in terms of x1 to xn, such that this weird looking equation holds true. What it says? That whenever there is an output such that satisfies the specification, if you replace y by the synthesized function in the specification, it must also satisfy. Remember the factorization case. If there exists a factor, non-trivial factor, so if you replace y by those non-trivial factors, should also satisfy the specification. So that is what the today's talk's focus is. Okay? What is the bird eye point of view? You need y as a function of x, such that they must satisfy this. This is a very fundamental problem in computer science called column functions, and this particular f is called column function vector. Why this is called fundamental problem, we'll see in 2 slides after this. Before this, let us another, yeah.
Aren't there already satisfiability solvers like Google's Autos? It has a constraint programming solver, CPSAT.
It is giving you one satisfying assignment. I'm talking about synthesizing.
Okay.
2 different aspects, right? We'll see the difference between the synthesizer and solving in some time. So let me give you one example here, right? Suppose you have working with 2 inputs, 2 outputs, 1 output, and your specification is very simple, just an OR of all the variables. What can be the possible column function? If I tell you that this is this column function, do you agree with me? So what you have to do? You have to replace y by this, and it should satisfy the specification. Is it satisfying the specification? Yes or no?
It is.
Look at the table. It is, right? That means it is one of the possible column function. Can you come up with something else? Is this the only possible column function? What happens if my function is negation of x1?
It is not a small.
Negation of x1 is not? Why?
Because then there is a possibility of x1, the third condition, being false.
No, so x1 or x2 or negation of x1. So x1 or negation of x1 is always going to be true. Right? You have to replace this y by the function. Right? That was the factorization problem. Recall that. Right? So there can exist multiple possible column function, negation of x1, negation of x2, 1. Just a constant function 1 would also suffice for this case. So goal at this moment for us is to come up with one such function. Only one. No objective saying that it should be smaller and any other optimization criteria. Just one such function. And this is still the hardest problem. It's a more fundamental problem in computer science. It has a storied history. It was studied by Skolem in 1920s and Hubbard in 1930s with the problem of decision, not the computability version, but the decision whether there exists a function or not. Actually, this history goes back to Bull as well, when he looked into this case with respect to the existential constant of Boolean unifiers. So this is indeed a fundamental problem, and if something is fundamental, then of course there has to be diverse approaches to solve this. So many approaches. But the biggest problem that we had was that none of this approach was able to scale for the practical scenarios. And that is where we had Manthan. Manthan works at the intersection of constraint sampling, machine learning and formal methods. How many of you know about constraint sampling? Formal methods, automated reasoning. It's similar, right? We can, I did not change my slide, I should have written automated reasoning here instead of formal methods. Okay? So, constraint sampling we don't know, we will see. Machine learning, how many of you know? Oh, all the hands. Okay. So, this part we will don't have to discuss then, right? So, only the constraint sampling and how we are doing the formal method, that we have to see. So, let me tell you about the architecture of Manthan. What it takes a specification as an input. You remember this was a logical relational specification. We did not have any data with us, right? And I said that I am going to use ML. For ML what I need? Data. Otherwise what I am going to do? So the first part for me is to generate the data using that specification which is given to me. So for that we are going to rely on constraint sampling. Okay? What is it? We'll see in a minute. Once we have the data, we can of course learn the candidate functions. Why not? So that is the second part. And once we have the candidate function, that can be 99.9% correct, but we cannot trust them. We want something which is 100% true, right? So we need to verify whether the candidates generated by the ML are indeed the functions that we wanted. And if not, we have to go into the repair loop. And that is where the power of formal methods / automated reasoning will come into the picture. Okay? And you need to see this, that this particular setting can be used in any situation. This is not specific to Manthan. LLMs can also give you some candidates. Once you have the candidates, these two parts will replace by LLM, and then you can use the verifier and repair loop to trust whatever the LLM is generating is correct or not. Right? So this is not specific to Manthan. This is a very generic framework that we are talking here. Okay? So let me first talk about this data generation component. Why? Because that might be useful for your problem where you do not have the data. Irrespective of the synthesis problem, right? You have some constraints in your hand. You want to solve those constraints using ML, but you do not have data, so you don't know what to do. And that's where these approaches will come into the picture. So let's see, how do we generate data? For data, as I mentioned, we are going to use constraint sampler. What is a constraint sampler? You remember at the beginning of the talk, I said that SAT solvers can take a Boolean formula and give you one solution. Remember x1 or x2 or x3. We got one solution, x1 being 1, x2 being 1 and x3 is being 0. But there are multiple solutions for this particular formula also. In fact, there are 7 solutions to the power 3 minus 1. All zeros is not a solution, rest all are solutions, right? So there are multiple solutions. And what we can do is that we can sample those solutions uniformly at random. So if you see, this bigger is all possible satisfying assignment 2 to the power n, the bigger circle. The smaller circles are the satisfying assignments. Not all are satisfying assignment. As you have seen, 0, 0, 0 will not work for x1 or x2 or x3. So the smaller circles are the satisfying assignments. And you can sample those satisfying assignments uniformly at random. And those sampling strategies called constraint sampling. There are tools available, scalable tools available to do that for you. Okay? For example, this is the same specification we have seen so far. I'm just conjuncting with the similar looking thing, right? And if you look into this table here, this is not all possible solutions, of course. There are many solutions which is not part of this table, but all of this is a satisfying assignment. So if you put x1 is 0, x2 is 0, y1 is 1. So this is true. Here y2 is 0, so this is true. So 2 and true is true. So if you put all of any of these row into this formula, this is going to be a satisfying assignment for that, right? So this table we can trust. Agree? So now we have the data. But is there any problem that you are seeing here with respect to this data? Let me tell you. For the same x, there can exist multiple y's that satisfy this specification. Yes or no? What should you pick? For this x1 being 0, x2 being 1, whether you should pick 0 or 1. Will it matter? What do you pick? If it matters, then what should you pick?
To satisfy the specification, it won't matter.
Agreed. But then the final goal is to generate the function. And you are going to use some ML algorithm for that. ML is garbage in, garbage out. Right? So you need to provide good data. That is why you are generating the data at this moment. Right? Will it matter for you whether if you have 0, 1? For this, whether you want to pick 1 or whether you want to pick 0. So currently we have this. What will happen? If you pass it to the some ML algorithm, you might get this complicated looking function. But for the same, as we have seen earlier, simpler function also exists. I said that we are not going to go for the simplest possible function, but I am going to change the scalability. Right? That was the holy grail, and that's why we are proposing this method. So if our data somehow we have this as our data, it will be easier for us to predict a simpler function. You will not be able to see this in a 2 input 2 output case, but think when you have 1 lakh input and 2 lakh outputs. This small change is going to make your life much easier. Right? So ideally, with a magical sampler, you would have loved to have these kind of thing. Why this? Because it has a choice between 0 and 1, and here at this particular row, it did not have any choice. So the 1 was forced. So I said, okay, wherever it was forced, I will just take 1. Right? Wherever it has a choice. Here in this row, the 0 did not have a choice. So wherever it had a choice, I will say I will take 0. But this you can see because this is a toy example. In a long run, you will not be able to see these things. You just have your formula in your hand, the specification in your hand, nothing else. So you cannot come up with this magical sampler automatically.
By this, we can miss some of the cases for verification.
Agreed? We are just uniformly sampling. We might, so we have to repair. You remember the loop had verification and repair. Or anyway, you can't trust ML. Right? So that's another thing.
There were places where it was 0 and 1 deterministically, and there was choice of making 0, 1. What would it pick? 0 or 1?
Deterministically?
Like in this, y2 has 0 value at the end. So wherever there was choice, you chose 0, 0, 0. Let's say the second row was 1. And
that is what I am saying. So here you can see, because this is a toy example, right? We had the number of satisfying assignments small. So you can create this table. Think about the case when you had 20,000, 1 lakh variables. You cannot create this table, right? So you will not be able to see. So you have to predict what to do. Again, ML will come into the picture. But before that, we have
Question: what is this a subset of all the possible rows? Or
this is all possible satisfying assignment. That we cannot see. This is just for the illustration purpose here.
I was wondering why the y2 is 0 in the last row.
because when x1 and x2 is 1, there is no choice for it to take. It has to take value 0 to satisfy this.
So why did we add that conjunction in the first place? That second
That
one?
is just a specification we are working
Oh,
with.
the
It's a
whole
toy
thing is-
example. Yeah.
Oh, I thought only that.
No. That was for the first toy example. Here, in order to showcase, I added this. So this is the latest specification. Okay. So this magical sampler is not with us, but something called weighted sampling is with us. I'm going to give you a very high level overview of in 2 minutes about the weighted sampling. If you are not understanding, it's perfectly fine. Okay? You can doze off for 2 minutes, but then you have to come back. Okay? So what weighted sampling is saying is that instead of uniformly at random choosing the satisfying assignment, I can have some weights to the satisfying assignment. You remember earlier everything was grey because I said probability of getting an assignment was equal uniformly at random. Now I'm saying that purple ones are more important to me than the yellow ones. So I'm getting more purples than yellow. It's a probability. So I can assign weight to the satisfying assignment and sample according to that weight. How do I assign weight to a satisfying assignment? Actually, what I can do is that I can assign weight to the variables. For example, we had x1, x2, y1, y2. So all possible polarity, x1 can be 0 and 1, x2 can be 0 and 1, y1 can be 0 and 1 because domain is Boolean. For all possible polarity, I can assign some weight. And what will be the weight of the assignment? Nothing but the conjunction. For example, 0.5 times 0.5 times 0.9, y2 is 0, so 1 minus 0.9. So probability of getting this assignment x1, x2, x1, y1 is 1 and y2 is 0 is proportional to this. So suppose if we had y2 as 1, of course the probability is going to be more. Right? So I can assign weights to the variables or literals very specifically such that the probability of getting that assignment is proportional to the multiplication of weights of that literal.
So how do you get those weights, or do you learn them from ML model?
Yeah, that we will learn from him. So there is a way, once we have those weights, we can actually sample according to their weights, but we don't know what is the right weight. And that's where we can actually use ML model. So what we did, we said that okay, because X are the inputs and input I want to sample uniformly at random. I don't want to bias towards the input. So weights of X's I have fixed always 0.5. Outputs is where I need the bias. So I said okay, let me just fix 0.9 first, sample something, small set. Let me fix 0.1 first, that is biasing towards 0, biasing towards 1. Get some data, club together, learn ML model what should be the right weight. And then use that weight to generate this. So
I missed the intuition behind the weights. What?
the weight intuition was this. Sorry. Yeah. If we just generate uniformly at random, right, we might get this complicated looking data. For this small case, also we will learn this complicated function. Hypothetically, if we had a good sampler, we could have learned a simpler function here. So in order to come up with this magical sampler, that's an attempt as a weighted sampling. So in that, if my weight for y1 was 0.9, that is I am biasing towards 1, I will get 1. Right? If I am biasing y2 towards 0, I will get 0. So that is an approach to come up with a magical sampler. I said that I have an approach called weighted sampling, but I don't know what is the right way to work with. And that is where ML will come into the picture to tell me what should be the right weight.
So you're going to talk about that now, how ML will.
Oh, I don't know. I have already spoken about it. Here. It's a simple, basic simple strategy. Saying that I'm going to sample something first which is biasing towards 1. I'm going to sample another set which is biasing towards 0. Club it and learn the function.
Is this Wxi equals to 0.5? Is 0.5
Is the weight. It's the weight for the x1. So probability will be multiplication, right? Like x1 is 1, x2 is 0. So then the multiplication 0.5 times 0.5
That
times
is for the whole
assignment.
But
Yeah.
for xi to get 1, is this 0.5 probability?
That
of-
one will so the probability of getting that assignment is proportional to the probability, right? The probability that you are going to calculate, and that probability calculation, these weights are going to be.
So I mean similar. So the weights are telling you the likelihood that if you set that to 1, the function would be, and irrespective of the other variables, the function would be
Closer.
satisfied.
Yeah. Function will always be satisfied because I'm going to use a sampler which is guaranteed to give me a satisfying
Right, but if
assignment.
you move in a function where, like, okay, so if the function to be satisfied, if the particular variable needs to be 1, I mean, if the function, the correlation between the function being satisfied and that particular variable being 1,
So
if that is high, that is then the weight
then
should
the
be
function.
high.
Yeah.
But this is not, but there is a commutatorial interaction also, right?
So that is where the picture will come in, it's a probability. So if you are not, if there is a probability, so even if there is a case where the y, suppose I set it towards the 1, but it has to take the 0, there will be some probability associated with that also that we can get. So it's a probability measure that we are saying. It's a likelihood that you are saying.
Yeah, so I'm saying, like, in the sampling process, so suppose you set the weight of something, let's say yi to 0.9. Now if you condition the weights of the other variables, given that their weights will now ideally should change.
Ideally,
but
that is what.
are you leveraging that somewhere in your
So,
sampling also? Or?
Yeah, so this compute weight will actually take care of it because here I am biasing everything to be 1. So even if suppose there is a variable which has to take 0, it will be part of it because there so it will backtrack. The solution will say that, oh, somebody is biasing me towards 1, let me take the value 1. It will go and say that, oh, does not exist a satisfying assignment with me being 1. I have to come back and have to take 0. So it will be part of your data here and which we will learn here in the QI. So let me move forward with respect to the data generation. There is a lot more to cover. I have 10 minutes. So let's go. This is the slide to tell you that many such sampling strategies exist. So you have to trust me that you can generate data. Okay? There is a sampler from my group called CMS Gen available, which we developed. You can use that CMS Gen to generate your data. So the key thing here to remember is, even if your specification is a formula logical relational specification, if you want to work with ML model, you can generate data. Okay? And that data will be trustworthy. There is no noise in that data. Every row in that table will be a satisfying assignment. Okay? Where it will be useful? Suppose you want to generate some synthetic data for any application. You come up with for those application what are the constraints, pass it to the sampler and generate the data. So that synthetic data will be a real world data now, right? Because it is going to satisfy provably the real world constraints. So irrespective of the Manthan framework, this particular setting of data generation is very important, that I believe. So let me move forward. So now we have the data generated. We would like to learn the function out of it. And this is the simplest part of this talk. What we are going to do, we are going to learn binary classification. We are working with Boolean 7-9%. So if I want to learn function for y1, let me just start with y2. What I can do, I can use the features of x1, x2, y1 as a features, label for y2 and then pass it to the decision tree learning algorithm and get a y2 in terms of x1, x2 and y. Right? Similarly for y1. I can pass x1 and x2 as a feature, valuation of y1 as a label and pass it to the decision tree algorithm to get my function. Might not be fully correct. I am not going towards the full exploration. Even if I go with respect to the full exploration, the data that I have is not enough. I have sampled some satisfying assignment, not all. 2 to the power n, many sample assignment can exist and n can be as large as 50 lakhs.
So again, you are looking at the output of the function and you're looking at the input and then you're asking it to binary classifier to say what the output is. But are you utilizing the structure of the function anywhere in your prediction to the ML model?
No, I'm not optimizing. I have used in the later versions of this particular bug, but the one that I'm discussing, no. Function, optimization, size and all that will come into the picture.
Like for example, x1 and x2 have certain relationship, right? And that relationship will change.
That
based
will
on
actually look, that relationship should be visible in the data in somehow. So I'm just relying on ML algorithm to give me that relationship. I'm not putting extra effort at this moment to come up with that relationship. So my function can look like this, right? How do I interpret it as a function? Of course, there are 2 paths which takes to the leap node 1. So I say path 1, path 2, x1 0, x2 0, x1 1, x2 0, and my function is nothing but the disjunction of those 2 paths. So I have my candidate functions there. Now comes the important part. How do I verify whether this is indeed the function that I wanted? How do I repair those functions if it is not the function that I wanted? And that is where
So should that be not x1 and x2?
x1
Oh, x1 not x1, that's
and x2. This path and this path. So let me, what I am going to do, I am going to again rely on the certification thing that we have discussed earlier, right? So now you remember the question that we asked in the certification is the system. Can it be the case that system do not satisfy the property? My system here is the specification given to me. The property is the function that I have come up with. So the call should be specification and not of specification where I have replaced y with the function. That became our property. It's a simple SAT call to certify/verify. If that call is okay, we get our function. If no, we get a counter example saying that for this input, the function that you came up with do not satisfy the specification. So I have one specific input in my hand and I can use that to repair. How? We will see. Again, lots of notation, right? Formal method people, some point or another I have to show you the notation. This is the formula. Specification and not of property. Property replaced by, in y prime replaced by the function that we have synthesized. Notice x is same input, different output. One in the as per the specification, other one as per the function that we have synthesized. Pass it to the solver. If solver says, here is a satisfying assignment. What does the satisfying assignment will tell? For this input, the y and y prime does not match. Right? If says, I can't find a solution, that means the function that we came up with is indeed the function that we wanted, because it could not find the input for which the y in the specification and the y that you synthesized does not match. So it is again a simple SAT solver call to verify. And once we have the verification, we would like to repair. But this is where another important aspect comes into the picture. So far, in program synthesis community, as well as people working with the LLM might also relate to me, is that as soon as the verifier says that, oh, this is the counter example that is not working, this is the counter example which you want to fix, we usually start with that counter example and try to fix it. But that particular counter example is one satisfying assignment, might not be the nicer one. Right? Might be some corner cases sitting somewhere. What you want is to find an example. If you fix that, you fix a lot of counter example in that vicinity. So what we do, instead of globally finding a good example, we try to find an example in the vicinity of already found example. So we do not start working with whatever we get from the SAT solver. We say that, oh, good, you gave us one counter example. Let me find another good, nicer counter example in the vicinity of it, such that if we fix that, I'm going to solve more counter example. It is a generalizable. And that is where I pose this question as an optimization problem. And people who know, I'm going to pose it as a max set problem. If you do not know, just take it as an optimization problem that I'm going to pose. For this input, how many y's I can satisfy? I try to maximize the y which I can satisfy for this particular input which the SAT solver gave me. And that is where how I'm going to find a good counterexample question.
Yeah, in the scenario for an edge case, right, you said it takes things in the vicinity. Right? It checks the counterexample in the vicinity. What happens for an edge case which is far out?
So then we'll start with that. So if the optimization problem says that whatever you have is the one.
Oh,
Right? Optimization can say that I'm going to stick with whatever I have.
But
Or I'm going to do.
How does it determine the edge case? Because
The solver will give you. In the end,
okay.
until unless solver tells me that all the inputs are covered, I'm not going to stop.
So it checks every single
Every
possible-
single time it's going to check. Right? So this is my thing. I'm going to look for the satisfying assignment for this formula. If that formula tells me unset, my job is done. If this formula tells me sat, I'm going to find a nicer counterexample and then look for the reason why that counterexample exists. People might not know. If they know, it's called unset core identification. So I use the unset core to extract out the reason why this counterexample exists, use that reason to repair it. And this loop continues until, see here, this loop continues until the formula becomes unset.
So why would it be unsat core? Because the formula is satisfiable.
Yeah, but then I'm saying that for this input my specification does not satisfy. So I have removed, so this formula E and G are two different formula here. That's why there are two different
So what?
representations.
Which formula
This
is
is
not
with respect
satisfiable?
to sigma. So which is with this, so X is the input and Y is the output of the synthesized function. They together does not satisfy, that is why the counterexample came. So that formula is unsatisfiable. So I look into the unset core saying
Which
that,
formula? Sorry, I didn't get this. Which formula is unsatisfiable?
yeah, I'm going there. So if you remove the first condition here, this, right? If you just look into these two, this is unsatisfactory. That's why the negation will become true and hence you get. So the phi in which binds. So this is my G. So if you remove this negation and this, so if you remove till here, this if you remove, this is my G. This is unset. If it was unset, it was false, then negation became true and I got a counterexample. So I just asked what is the reason why this counterexample. So here is the architecture, right? I might have lost you in a couple of points. But things to remember, things to take home, right? AR, automated reasoning, and formal methods, FM, can be used to come up with a counterexample, come up with a nicer counterexamples, come up to repair the model system that you have in your hand. Okay, these are the 3 points. If you have a logical specification in your hand and you want to generate the data, you can do that. If you are working with any specification, any application, you want to come up with synthetic data, you can do that using constraint sampling. These are the points I want you to remember. Rest all, I am sure you are going to forget. So, as I said, we took up the challenge of scalability, right? So this was the results before Manthan. Y-axis is the total number of benchmarks. X-axis is the time taken. And these were the tools from different approaches, different groups before Manthan, all doing scholar function synthesis. No, none of them used ML beforehand, because we were working with the logical specification. If you noticed here, if you look into this point, it says that Cadet solved 280 instances. Each of them took less than and equal to 500 something seconds. Where does Manthan stand? Here. Manthan was able to solve 509 instances out of 600. And what we noticed is, and which is important, and you will not be able to see in the plot, is that the candidate generated by ML was very close to the exact function, but not exactly the exact function. So we had to go into the repair iteration, but not more than 30 times. And when I say 30, we worked with more than 30 lakh or 50 lakh, exactly I don't remember, variables. But in output variables, input variables are separate. That means 50 lakh many functions we had generated.
So where did you get, so I see there are 2 optimizations, right? One was learning the correct weights and then you did something intelligent for finding the counterfactuals also. Which one gave you more of the impact?
The nicer counterexample. That is actually the key. And there are many which I did not discuss. There are little bit engineering effort that we took. Rather than like generating 50,000, we clubbed some which we looked similar and generated that much. And there are multiple.
So if you improve the ML model more, do you see that having, like you use as a binary classifier you said, right? But better models that improve the prediction, do you see that having much of an impact, or you think it can have some small impact but it's kind of already saturated?
No, this benchmark set, now people have added many more. This is 2 years before. There are many more benchmarks, and that's why Manthan is not performing good at this moment. So ML model will actually make an impact. So, does not match. There are multiple such areas where 5 minutes, thanks. Multiple such areas where automated reasoning and AI can come hand in hand to make further improvements. And my group works in these areas. These are not exclusive, there are many other areas as well. And I'm looking forward to hire interns, PhDs, MTech, MSI students. So if you are interested, please do reach out. Just mention that you have attended my talk in the workshop here, and I will pay more attention to your email and then we'll reach out to you again. So these are some areas apart from the synthesis in which I work. Since I have 3-4 minutes, I'm just going to go into the recent work that I'm doing. LLMs came into the picture now, right? Why do we have to go with the decision trees now? So when I say LLMs, we don't have to specifically constrain ourselves to Booleans also, right? So I can have programs, functions, input specification. LLM can give me the first-hand candidate functions, right? I can repair them, verify them. If the verification says no, either I can use that counterexample and prompt again to the LLM, but at some point it might hallucinate. I don't know whether we are going to the right direction or not. So what should we do in that case? Should we repeat this loop or should we go here? We have no idea. We have a couple of works related to this under submission which specifically works with respect to some unknown function. For example, in this specification here, the bar, suppose you don't know what this bar is doing. Source code is not available because of many reasons, too large, proprietary, whatever it is. You don't know the bar, but what you know is the signature of the bar, that it is taking a y and asking some x. And then there is some post condition on this x and y. So now you want to come up with a function for bar. How do you do that? For example, there is an input x which is 19. I don't know what is the while condition, but in this while condition x is equal to x minus 1 every single time. Then I am calling some function f. F is returning y. And finally I have assert that x less than equal to y. Right? One toy solution could be y is greater than equal to 42. 42 is just number. Right? Irrespective whether it goes or not, the maximum value x can take is 19. So this is always going to be satisfied. But what we want is the strongest possible situation where we say that y is written has to be 19. That will also suffice. We don't have to go to 40 to 49, 50,000. How do you do that? Using LLM. So what you can do, you can generate candidates using few short plus precondition. Use program verifier instead of SAT and SMT solvers. And instead of repairing using the prompt, you can actually do the two-phase refinement where you generate the first takeaway that we had was that we will not look into the example that we get. We will try to find the nicer counterexample and use that to repair. With that, I conclude. And now open for questions.
So I have a very vague question. So for the last problem you talked about, the first one, so the problem was represented in the Boolean algebra. So how do you think the process will change if we work with, for example, like linear temporal logic? So there will be more symbols and...
See, the approach will work no matter what, but the scalability will come into the picture. Another thing is that do we have a verifier which can verify for the linear temporal logic, linear integer arithmetic, linear real arithmetic? We do have. If we have, good, right? The another thing is that we are repairing using some maxsat calls and unsat core sort of a thing, which is trying to extracting the reason and trying to optimize it. If we have these tools available for the domain that we are working with, we can use a similar approach. So what my general answer here is that the approach is there. We need to develop a lot more tools and achieve scalability to go over the different domains.
The idea of solving the current problem that you're working on, the idea of using LLMs to generate programs, you are working in you're verifying the output and then trying to send to the LLM, or perhaps if it hallucinates, leaving it altogether?
I'm looking into two-phase refinement, so I do not send it to the LLM directly. I actually try to solve it locally, and at some point I see that, oh, too many repairs, I say LLM, give me another candidate function, not working with this. So this is like a fusion between LLM and the repair. We can take it offline, I think, so with respect to the time.
The organizers.
Oh. Thank you.
Okay, our next speaker is Professor Sayan Ranu. He holds the joint positions of Nick McKeown Chair Professorship at the Department of CSE and the Yardi School of AI at IT Delhi. His research interests span the broad area of machine learning and data mining for graphs. Sayan has received several awards and recognitions, including the ACM India Early Career Research Award, Honorable Mention, and INSA Associate Fellowship, and Early Career Research Award at IT Delhi, and many more awards. So, Sayan regularly serves in the program committees and review panels of many journals and prestigious conferences. So, we welcome Sayan.
Thank you. Am I audible at the back? Okay. Yeah, so thank you again for inviting me here and giving me an opportunity to talk about some of the research that I am doing. Let me just quickly check if which one is. Yeah, okay. So again, I'll just start with a brief survey. So I know many of you now today, know machine learning, which means you probably take courses or just on your own, just try to read about neural networks and so on. But how many here are familiar with graph neural networks? Okay, 1, 2, 3, maybe. Most of you are not. So that was my assumption. So I will, before we try to explain graph neural networks, we need to know what graph neural networks are, right? So we will do a quick overview of graph neural networks, and then we will think about explaining and what does that mean. And in a way, it is also kind of flows nicely with the previous talk, because that was also about getting trust on the system, and explainability is also along the same lines, but although the methodologies may be somewhat different. Okay. So first of all, why graph neural networks? Before you go into graph neural networks, see why are graphs important, right? So as you can see here, graphs are used to model many different data from many different domains. So some of the we have collaborations with many of these companies. So for example, financial transaction networks is one big area where graphs are used to model what is going on, right? So we have one collaboration going on with MasterCard, and they are trying to use graph neural networks to understand when to give you a phone call and see whether you have genuinely made that particular transaction or not. So you may have received that, right? And why do they do that? They want to ensure that whether this is a fraudulent transaction or it's not a fraudulent transaction, right? Similarly, we are also trying to set up something with GST, which is a GST tax network, to identify frauds. Other domains, for example, materials and molecules, right? I think these are materials and molecules, right? These are again graphs. I mean, you can model them as graphs. The atoms are the nodes and the atom-atom edges are the bonds, right? And then you want to discover new drugs or come up with better materials and so on. Again, typically machine learning here would do a job that Priyanka was kind of saying in the previous talk. It will not give you the solution, but from a large candidate space, it will come up with very good candidates. And then the domain scientists will come and refine them and kind of come up with the actual solution. So they are not an end to the solution, but they are part of that pipeline, right? And then very interesting, of course, I mean, a big application here is in recommendation engines, what to show. Like when you're doing, Spotify, YouTube, what is the next item that should be shown to you, right? That is again a graph. It's a bipartite graph. You have users on one side, items on the recommendation candidates on the other side, and if one user clicks or is interested in that, then that's an edge in that particular graph, right? And then finally, neural networks themselves are graphs. And there are many interesting things that are kind of coming up right now, where you take the neural network as a graph, and that is the model is your data, and then you try to do something on top of that. Okay, so there is a lot of data that gets modeled as graph, and therefore you need to do some prediction, something on top of it, and that is where graph neural networks come into the picture. So who uses graph neural networks today? Many companies, right? It is extremely popular in the sciences domain. So many of the drug discovery companies, they are all using graph neural networks, and also in the for material discovery space. Social networks, no surprise, a social network is a graph. So friend recommendations and so on, they are all primarily powered by graph neural networks today. And then Google, why? Google Maps, right? How does the traffic congestion develop in a particular network, right? That's again a graph neural network that is in the backend. And then finally, financial transaction networks and Uber and Airbnb, Spotify, all these recommendation engines and so on, they're all being powered by graph neural networks. Okay, and when you are using something in powerful applications, of course you need to be responsible for that, right? You do not want to make predictions and not know when those predictions can fail or why certain predictions are being made, right? And this is exactly where explainers come into the picture. Okay, what is an explainer? An explainer here is, so first of all, what is a black box? I think you should be familiar now with the black box. Anything that makes a prediction, but you don't know why that particular prediction is being made. That's a black box, right? And what is an explainer? An explainer allows you to understand, or it helps you to understand why that particular why the prediction was being made. So it's essentially making the black box a white box. That's the sort of the overall objective. Why do you want to convert a black box into a white box? There are primarily three motivations, but there can be other reasons also, right? The first one is just the general thing, like if you know what the correct reasoning process is, right? Then is the correct reasoning process being made by the particular black box, right? You want to validate when you know the correct reasoning. And if you don't know what the correct reasoning is, then you want to uncover what is the reasoning that the black box has learned to make the predictions. For example, you have trained something and that is extremely accurate, right? But you don't know why is it accurate, what is making it so accurate. So let us take a look at it, and you want to see why certain predictions are being made. Let's give a concrete example. For example, drug discovery, right? You are given lots of molecules, and you want to identify molecules that are active against a particular particular disease, or for example, it binds to a particular protein target. And you train a classifier, and that does fairly well, right? But you want to know why, what kind of functional groups or what kind of structures is it really looking at to identify why it is particularly binding to this particular protein target. Because once you uncover the black box, then you know more about what is going on, and then you can design new molecules that has those desirable characteristics, right? So that is the reason why you want to know insights. And then finally, you also want to know when it is making an incorrect reasoning. It may be accurate, but maybe doing a reasoning that is not correct or not fair. And I'll give you a real life example. This happened in American Express, where a couple applied for the same credit card, and the credit card was, and they had similar sort of profiles, and the credit card was actually approved for the male, but it was not approved for the female, right? And this became a big news because gender bias was being used. And then they had to sort of and now once it happens and it comes up into the media, for the company, they also don't know what to do, because you cannot just retrain a model from scratch right away. It's a big problem. So before you go live with a model, you would like to know whether there are certain biases that have crept into this particular modeling pipeline. Why does it happen? Sometimes correlations become biases, right? For example, if there is a in your data set itself, if there are certain correlations that males have a higher income and females have a lower income, instead of the model, instead of looking at the income, it starts looking at the gender, right? And therefore, it starts using gender as in the reasoning process instead of the income. And now, even when you have two data points that have identical or similar incomes, just because of the gender bias, it makes a wrong prediction, right? So in your training data, it was fine, but there is one example, right? On the average, it may still be doing very good, but if that one example where it shows bias and that comes out, right, it's trouble for that particular company. And in fact, it should come out. You should not be using such biased, reasoning pipelines. So this is why, again, explainers are important, right? So what we are looking at here, I think what Priyanka was also talking about, right? There are two kind of ways in which you can handle an ML model. Something that is built with certain principles ingrained with it, right? For example, it is a trustworthy system, you have built it like that. The other one is post hoc, in the sense it has been built, right? You don't know how it has been built, but in a post hoc manner, you are trying to explain what is going on, okay? So we are going to look mostly at post hoc explainers rather than those that have been built with explainability ingrained into that particular system. Both of them are important. In an ideal world, you don't want a black box, you want a white box in an ideal world. But the fact is not everything is ideal. People are training these neural models or LLMs and they are being deployed, right? So the challenge here is that when something has been deployed, how do you go and uncover them or learn as much as possible about them, right? So this is why you want to, post hoc explainers are perhaps not what you need in the ideal world, but in the current world you actually still need them, okay? And then finally, what is a good explanation, right? A good explanation has two primary characteristics. One is that the explanation should be faithful to the particular black box, right? What do I mean by faithful? If the explanation is saying, okay, this is the function that you have learned, right? Is the output of that function similar to the function that similar to the prediction that the GNN is making, right? That is called faithfulness. The explainer is giving you the same prediction as what the neural network has done, and the explainer's predictions are all white box, okay? The second one, which is very important and has got very little attention in the research community, is understandability, right? Explanations are consumed by humans. So if I give you an explanation that when I read about them, I don't even understand what is going on. The explanation may be there, it's a function, right? But I have no idea what this function is doing, it's too complex, right? Then that explanation loses its purpose, right? So therefore there are two things. One is the faithfulness, the other is the ability to understand what the explanation is, right? So no graphs over here, this is just generally sort of explaining what is an explainer as such. So any questions so far? Everyone fine? Okay. Right. So therefore, now we will go into the domain of graphs. Okay. So how do GNNs work? And I will go slowly. If you have any questions, feel free to stop me. Okay. You don't have to wait till the end. Okay. So how do GNNs work, and how do you and what do you use them for? Those are the two questions that we want to sort of understand over here. So the first thing, we'll start with what do you use them for, right? So suppose you have a graph. Okay, here is a graph over here, and suppose you have labels on every node in this particular graph. Okay, so for example, the colors here are the labels. Okay, so you have some nodes that have purple labels, some of them orange, and so on, and the gray nodes are the ones where you don't know what their labels are. Okay, so now can I learn a model that can tell me what are the labels of the gray nodes? Okay. So essentially this is called what? A node classification problem. You all know classification problem, you have data points and some class labels. Here the data points are essentially nodes in a particular graph. Okay. So what is the application over here? Let's go back to the financial transaction, right? You have certain nodes that are fraudulent and certain nodes that are not fraudulent, right? So you have some label data, okay? And now you want to identify which are the other nodes that for which you do not have labels, whether they are engaging in fraudulent activities or they are not engaging in fraudulent activities. And what do the nodes here mean? The nodes here could be credit card transactions, right? Or tax tax invoices generated. And the edges are who has transacted with whom, right? So this is the graph, and then you have this predictions, right?
You want to minimize something, you want to optimize something in the prediction?
You want to optimize the number of misclassifications.
No, but here there's no classification to begin with, right?
No, it's just a traditional classification pipeline. So what you have here is that's okay. So let's first think about a regular classification problem, right? What do you have? You have, let's say, high dimensional feature vectors and a class label, right? And then I train an MLP that using some loss function, let's say binary cross entropy or any cross entropy loss for multi-class class classification, you get a prediction. I want to train the parameters of the neural network so that my loss reduces. Okay? Here what do you have? Here you think about, you have the high dimensional data points, right? So for example, for every user in a social network or in a financial network, you have some attributes. What is the average income? What is the age? Or how long a business has been operating? What is the address? Where is it located? All those things, right? So you have some attributes at every data point over here. But in addition, you also have some relationship between the attributes. Sorry, not the attributes, the entities. Okay? So now, some of these nodes have class labels associated with it. Some of the nodes don't have class labels because they are unknown. So I want to know what is the label of these ones. So I want to learn parameters that can take the node attributes and the topology of the graph and can make a prediction on these gray nodes. Okay? So it's just like training an MLP. Here we are trying to train a graph MLP. I mean, we'll see what the graph MLP or graph network is about. So it has some parameters, right? The only difference is an MLP cannot take topology as an input. It can only take the attributes. Here I want to take the attributes and the topology, both of them jointly, and then be able to do a prediction that jointly kind of uses information from both these domains or both these modalities. Okay? So it's a classification problem, right? But you can have other problems like link prediction, and we'll see one about graph classification. Any other questions on this particular slide? Okay? Right. The next one is another application, potential application, is graph level task, right? So previous one was a node level task, which is you are doing some prediction on the node. And I gave you one more example earlier that you may want to identify molecules that show a certain binding activity, right? So what is that binding activity? Suppose you have certain molecules and every molecule has a class label associated with it, right? Whether this molecule is binding to a target protein or whether it is not binding to a particular target protein, right? And now you have, let's say, a database of hundreds of millions of molecules, okay? And you want to now cure a particular disease, okay? And you want to identify from these hundreds of millions of molecules which one should I actually filter out and then do further experiments in the lab, right? What do you want to do? You want to first do a classification, okay? Or maybe a regression also, potentially, right? You want to do a classification that which are the molecules that show activity against this particular protein target. If it is active, it is predicted to be active, then I will do the further tests over here, right? So here you have a graph as an input, not nodes. You have many graphs and each graph has a label with it and you want to do a prediction of it. Okay? So just like you're replacing your high dimensional data points with nodes or graphs and so on, right? So there's a structure associated with every prediction that you are making. Any questions? Fine? Okay. Right. So now the question is, how do you do this? Let's now think about the technical details. So what is the what is the methodology behind this? Okay. So what you do here is ultimately you want to embed every node into a high dimensional feature vector. Just like you do in an MLP, right? You are given some, let's say, d-dimensional inputs and you map them into some d-prime dimensional space and then you do a certain classification or something in the final layer. This is exactly what I want to do. Okay, I want to map every node into a high dimensional feature vector. How do I do that? What do I need to do this, right? So this high dimensional feature vector should jointly encode both the topology as well as the attributes at every node, because every node not only has the topology but also the attributes with it. Okay, so here is the sort of the problem formulation. So just to sort of make sure everyone is following, you have a graph G as an input. Okay, the G is composed of V, E and X. V is the set of nodes, E is the set of edges and X is the set of attributes. Okay, and when you are training it, you also have some training data associated with it. What is the training data? If you are doing a node level task, for example, fraud detection, right? Or what friend recommendations to do in a social network, something of that sort, right? In that case, every node is associated with a label for that particular node. Okay? If you are doing a graph level task, then you don't have the node level data, you have a label with every graph. Clear? Any question? Okay. So now what happens? So what happens here is, therefore, you take this original network, you embed them into some embedding space. The objective here, we'll look again into the details, the math exactly. The objective here is that two nodes U and V should have similar embeddings if the predictions for them are similar. Right? If both of them are going to be positive or show a positive effect in terms of a particular class label, whatever classification, then they should have similar embeddings. And if two nodes belong to a different class label, then they should have dissimilar embeddings. Okay? And once you have this particular embeddings over here, then it goes through some particular aggregator, which is another neural network, or it could be a simple pooling layer. For example, if I am doing a graph level task, right? So GNN would always embed only the nodes. It does not embed the graphs. It would always embed the nodes into a high dimensional space. So now suppose I need a representation for this graph, right? A graph is composed of a bunch of nodes. So what do? I can do an aggregator. The aggregator could be, okay, I take the average representation of all the nodes in that particular graph, simply average. Or I can do a sum of all the embeddings of the nodes in that particular graph, right? Or this could be a neural network using attention and some complicated stuff, right? So once you have this, it's an optional. It depends only whether you are doing a graph level task versus a node level task. And after that, you have an MLP that takes this embeddings and does the final prediction, right? So for example, if you are doing a node classification, you would do this, and like any standard MLP, right, you would take a dot product with a vector that this MLP learns, brings it down to a scalar, and then you may do a sigmoid activation. Okay, clear? Any question? Everyone following? So where does the magic happen? The magic happens in the GNN. So what is the GNN doing? So this, so far, this is just standard neural network. You think about some modular structure here that gives you embeddings, nodes into embeddings, and once you map nodes into embeddings, you use the standard neural network machinery over here, right? Nothing special is happening. Okay. So let's now think about what is going on in the internals of the GNN. So what happens in a GNN is I want to use the topology, I want to use the topology as well as the attributes. So what happens is in a GNN we use something called a message passing algorithm. Okay, message passing paradigm. So what is a message? So let's focus on this particular node A. Okay, so A receives messages from all its neighbors. Okay, who are the neighbors? B, C and D, right? So I receive a message from B, C and D. Okay, similarly B receives messages from B's neighbors, right? Who are B's neighbors? A and C, right? So you have two neighbors over here. And C receives messages from C's neighbors, D receives messages from D's neighbors, right? Once I receive the message, then what do? I kind of aggregate them in some particular manner. Okay. So now what are these messages? These messages are, and what are these neighbors? So what happens here is, suppose you have like in a MLP you have number of layers, right? Layer 1, layer 2, it's we call it a deep neural network or something, right? What deep means essentially translates to the number of layers that you have. So in a GNN you also have layers. Okay. So if you have a 2-layered neural network, what happens here is that in this particular, here this A, it receives messages from B, C and D, right? And B again receives messages from A and C and then A, B, C and so on. What are these messages? In layer 0, this is my layer 0, this is when the entire thing is starting. In layer 0, the messages are nothing but the original feature attributes that you have for every node. Okay? So like gender, age, whatever the attributes that you had. And then in layer 1, what do? I take these messages and then I aggregate them in some way. What is an aggregate? Let's think about aggregate as an average. Okay? So I will just take the average age, average, let's say location. I mean, it's hard to say what is a location, average of a location, but average of everything, we'll come to that. But average of all the attributes over here, and then I store it over here in B, right? So now in layer 1, so B's initial representation was XB, right? But in layer 1, B's representation is an average of my neighbors. Okay? And now look at A. So A receives messages from what? From B, C and D. But the message from B is no longer XB. XB was the original representation of B. The message from B right now is the layer 1 representation of B, which is already updated with the average of its own neighbors, right? So in other words, if you have a 2-layered network, you can think about it roughly as A's representation is a function of its 2-hop neighborhood. Because if a node is outside this 2-hop neighborhood, the message will never reach A in 2 layers. Okay? So you can think about it that the embedding of A is a function of its 2-hop neighborhood. That function could be just simple average, but it's not simple averaging. There's slightly something more intelligent that you can do, which is you fit, just to sort of tell you, here you fit an MLP, or in this box you fit an MLP, right? You take the messages, you may do an average or something, and then you pass it through an MLP or any neural network. Typically it's an MLP, it could be any neural network. So what is this MLP going to do? It's going to identify which are the features that are important for my task, which are the topological. For example, C may not be that very important, and A is more important, right? Which kind of neighbors are more important, and then filter out the unimportant messages and then pass on only the important stuff to this A from over here, right? So it is like you start with the raw information and then you process them throughout the useful one. I mean, keep the useful one throughout the the not so useful information, and then you pass it on to the next round. Okay, but all this is restricted within the 2-hop neighbors if your neural network is 2-layer deep. Okay, so what is this, right? So what I show you here is a basic version of a graph neural network. So what you could do here, I was saying average, right? So initially your feature is just your original attributes. Okay, so let's just go slowly with this particular equation. The feature is just these original attributes. In any layer k, so if let's say k is equal to 1, okay, if k is equal to 1 and v is a particular node, what you do here is you take the average. So this is like I take a message from each of my neighbors, nv is in each of my neighbors. I take the average of this of my neighbors' messages, and then I do a linear transformation. This is a learnable weight from the MLP. Okay, and this is the bias term. Clear? Any question on this particular one? So this is standard MLP equation. There is nothing that we are doing more than that, right? So what we need to learn is this W and this BK, which are essentially the weights of this particular neural network. So this happens in each layer, but this you continue doing this in each of the layers. So you have a WK for layer 1, you have another weights for layer 2, and so on. Okay? Any question so far? Okay. I hope I am not completely losing you, but if the main thing to sort of remember here is that at every layer I am taking an average or something of that sort and doing a linear transformation followed by nonlinearity using an MLP equation, right? So that is the simple. Fine. So this is the basic GNN, right? My GNN predictions are a function of my L-hop neighborhood if I have L layers deep. So now therefore the question is, what do you mean by explaining a GNN? Because again, if you pass these messages to an MLP and you learn some weights, I have no idea what these weights are learned and what kind of predictions we are making. So what do you mean by explaining GNNs? So let's take an analogous example from vision, and then we'll try to sort of see how it maps to in the domain of graphs, right? So in a vision, for example, if your prediction, so let's say I want to do a prediction of what is the animal in this particular picture, right? And let's say you have a convolutional neural network that makes a prediction that it's an Australian Terrier, right? So now you have to understand why. Why did it make this particular prediction? Well, there are certain techniques that say, the neural network, you generate a heat map on this particular image, and it shows that the neural network focused more on this particular regions, right? And therefore, it predicted that this is an Australian Terrier. You don't know the entire details like why it was predicted an Australian Terrier, but at least you know that the neural network is focusing on the right places, right? Again, it's not fully interpretable, but it gives you some particular confidence. So now, in the context of a graph neural network, what do you want to do? So suppose you have many graphs, and it makes a prediction that this graph is positive or negative with a particular activity, right? You want to know what is the subgraph within it that is important towards a particular prediction, right? So in the context of a molecules, it could be functional groups, right? Or similar such structures. So here you may say that this is the prediction that it got. The highest amount of importance was given to this particular fragment over here, which corresponds to be over here, right? And similarly for this one, it is it is this one, and then similarly for this, it is this, and so on, right? So this is actually what are called local GNN explainers. You take an input and the output is subgraph within it that has the highest importance towards that particular prediction. Okay, this is an explanation. However, local explainers have a certain problem. The problem is that every explanation is being made independently. Okay, if I have 10,000 graphs, I will get 10,000 explanations, right? So I take this graph, I make an explanation. My explainer tells you what is the most likely, the rule that has produced this, right? But now if you think about any classifier, not just GNNs, any classifier, I don't learn a parameter space that is specific to each of the input data that I have. I have learned some global function. I have learned a single function. That function is hidden from me, or the function is too complex. It's not hidden. You can actually compose the weights and you can know what the function is, but it may have no semantic meaning, right? So I know I've learned a single function, and that single function is being applied to every inference instance that I am doing, on which I am being doing, right? So therefore the function is common across any prediction that I am making. So local explainers, they are not consistent with that particular design of neural networks. What they are doing is they are saying for this is the prediction, for this is the prediction. But I am learned a single function that is getting applied to everything, right? So this has motivated the movement now towards global explainers. What is a global explainer? Given a black box, it learns a single logical rule, ideally a logical rule which is interpretable, and that single rule is applied to every prediction, that every inference instance that you want to sort of every instance that on which you want to do inference, right? So it's not like you are giving a different explanation for everyone. It's a single white box rule that you apply to everything, and the objective is that the prediction of the white box rule is consistent with the prediction of the GNN or any black box, right? So this is called a global explainer. So now, this is sort of like the taxonomy of explainability just in the context of GNNs, and there's a lot of other explainability works that have happened. What I want to sort of highlight here, that almost the entire work here has focused on local explainers, right? And global explainers is something that has kind of, still, given how quickly ML moves these days, I mean, there's still some works over here, but it's still much less saturated compared to what people have done in the local explainability space, right? And this is natural that we want to go in this direction, because that's sort of making it more consistent with the prediction mechanisms of the underlying black box models. Okay, so we'll quickly go over this, right? Now, why do you want to talk about global explainers, right? So there has been some work done, but no, it's not complete, right? And I'm not criticizing just everyone's work. I mean, even we have also worked on this particular domain last year, right? And these limitations that I'm going to talk about, that applies to all these papers. I mean, our work and this one. So the typical, so far what people have done for global explanation, which is a harder problem, is that they have made some simplifying assumptions, which is okay to get started. What are the simplifying assumptions? It works only for graph classification, and that too only for situations where the nodes have just labels and not feature vectors. Okay, and what is a common example of that? Molecules. I mean, okay, so this is, yeah, I don't want to come here yet. Molecules, right? So molecules, what you have a graph and you have carbon atom, oxygen atom, right? You don't have rich feature vectors associated with it. Now contrast that to, let's say, for example, recommendation engines or financial fraud detection. Every node there has attributes that tells you, what is the number of transactions that you typically do, what is the domain in which the business operates, where is the business located, right? All these kind of different features are there. So none of the explainers are work in that particular domain. And why is that? The reason is all the explainers, I mean, there are not too many, all of them have a certain common assumption. They take the input graph, okay, and then they identify which are the important subgraphs within those important graphs, right? They can do that using local explainers that I talked about. They sometimes do it using Shapley values, frequent pattern mining, all these kind of classical algorithms that people have already used, right? Once they identify these important subgraphs, what they do is they convert that into a binary vectors. If the important subgraph is present, then that particular dimension is 1. If the important subgraph, so it's similar to what Priyanka was explaining in the previous one. You have this x1, x2, x3 inputs, and then you have some certain outputs. So you can think about this at all the x's, right? You have this binary feature vectors, and you have which is 1 if the particular corresponding important subgraph is present, and if it is not present, it is 0. And then you learn some logical formula, typically a Boolean logical formula, over these subgraphs, so that the output of this Boolean formula is same as the output of the GNN, the graph neural network, right? So therefore, this thing is now completely interpretable. You know what are the functions that are important, how their presence absence is being used to encode, and now you can work on this. The problem is, this pipeline breaks when you have rich attributes, and when you have massive graphs. I mean, this fine over here, like over this, but when you have massive graphs like over here. Why is that? The main reason is reliance on something which you call subgraph isomorphism. What is subgraph isomorphism? Given a graph, given two graphs, graph A and graph B, you want to identify whether B occurs within A or not. Okay, that is called the classical subgraph isomorphism problem. Other than the fact that this is an NP complete problem, just subgraph isomorphism is hard to define in the context of complex networks like this, because when you have hundreds of attributes, right, a same recurring subgraph which has the exact same attributes in all these neighbors would never happen. You would never have a same recurring subgraph. You may have something similar but not the same recurring pattern. So that is the crux why the current global explainers, when applied to complex networks like this, it just breaks. Okay. So therefore the question is, what do we do over there? And that is not the only problem. The second problem is these Boolean formulas over molecules where you have small functional group fragments. They are easily understandable in the context of molecules. But when you go in the domain of like complex networks that have millions of nodes, right? How do you even explain them with subgraphs, right? I mean, you have certain nodes and certain attributes. It's very hard to even explain them from a topological perspective. So it's not only breaks the faithfulness, but it also breaks the understandability. So both of them are essentially problems, right? So interpretability as well as the faithfulness. So how much time do I have left? Can I get a quick time check? 50, good. Okay. So therefore, what is the summary of the main problems, main issues over here? So current pipelines are based on recurring structures. You don't get recurring structures in complex networks. They assume just scalar features, or like simple node labels. You don't have that in complex networks. And then a very, very high cognitive overload, in the sense even if you can come up with some explanations, that explanations may not be understandable by humans, which is very, very important, right? So we want higher level concepts, right, over here, the ability to deal with rich features and interpretability. How do we do that? So just as an example, right, suppose we have a complex network like this, okay, and one of the common data sets that we looked at are called citation networks. So this is again a node classification problem. Every node here is a paper, okay, and an edge here is if a paper has cited another particular paper, and the class label is what is the topic of that particular paper. Right, it could be, let's say, machine learning and databases and formal verification and so on, right? And typically these nodes, they also have rich attributes, which are typically, let's say, the word vectors of their abstracts, okay, or the titles, something like that. So now, if you want to sort of say that, okay, let's take a particular node, let's say this particular node over here, the one with a white circle, why is this being predicted into the class of probabilistic methods? Let's say that is the question, right? It's a correct prediction, but why? The ideal explanation would be something like this. It's called a probabilistic method because it includes keywords like Bayesian network, Markov chain, density estimation, gift sampling, like which are sort of comes from the attribute space, and at least 20 to 80% of their one hop or two hop neighbors are also probabilistic methods. So it cites other papers from probabilistic methods, and it has certain keywords that also say that these are these words are associated with probabilistic methods, right? So this is a very nice explanation, something that I can understand. Now why is that? The reason is because this is in plain natural language. That is one, and it kind of looks at the distributional aspects of what is going on in the attribute space and in the topological space. Now if I just show you the two hop neighborhood around it, I have very little way of understanding what is going on, right? So this is ideally what we want to do. Natural language explanations for explaining graph neural networks. Right? And how do we do that? So for this, we went into the domain of something, we took inspiration from something called exemplar theory. So what is exemplar theory? So it is kind of rooted in cognitive psychology, and the idea here is, we as humans, we often categorize or explain things based on some past stimuli that we already have, right? So for example, we can say, this workshop is very similar to another workshop that I had over there, right? Or this particular person is a fraud because I know another person who had similar characteristics as this person, and that person turned out to be fraud. Right? We use this kind of comparison with some past experiences to sort of say that this particular person may be in this particular category, right? So this is something that we routinely do. And our idea here was that if we can use exemplars to sort of explain, then that would be something that be useful for humans to understand the explanations. Okay? So generally, therefore, what is an exemplar? An exemplar exemplifies prototypical characteristics of a particular population, right? And a general class distribution can have multiple exemplars. Like all nodes in a particular class may not have the same exemplar, but there should not be too many exemplars also, right? You should be able to characterize them within some order. And secondly, like so the shared characteristic of the exemplars population, that all the population within a certain exemplar, right? So this exemplar represents other many such similar nodes or population. They should share similar characteristics. They should not be something that is very different, right? So what we want to do is we want to identify these characteristics using a particular Boolean function. Okay, what are those characteristics? Yeah.
This is similar to what you are doing in a subgraph, right?
Exactly. This is very similar. So we don't want to move away from it, but at the same time, you want it to scale to rich attributes and be able to handle complex networks. Right? This is very similar. There also we use Boolean formula here because Boolean formula is something that works. So we don't want to do away with that. The question is how do we reach there while staying within the complexities that we have to deal with. Okay. So what is an exemplar over here? Just another example over here. So this is for a mule detection in financial networks. So mule accounts typically they are used to sort of transfer money to to other accounts while staying as undetected as possible. So one of the common signatures is that this transfers small amounts of money which has a certain under a certain particular threshold 20 to 30 times per week, and mostly to accounts it has no prior relationship with. Right? It's not like it's transacting with someone who it has transacted with a lot in the past, right? Quite a few times with other people. Yeah.
I mean, if one little question, if a global explanation is possible, isn't that the solution? Why do I need a GNN at all?
Absolutely, that is the thing, right? So people don't use these explainers; they train their models. In an ideal world, you want a white box model, but that's what not people are doing. They are training these models. And then when something happens, they want to know what is going on, right? That is one of the main reason. And the other thing is this explainers. There is a subtle point here. The explainers are not trying to predict the data. The explainers are trying to predict the prediction of the GNN. Okay, which means if the GNN is performing poorly, we want the explainer to also perform poorly. We don't want to explain the data. That is not the objective. So when the GNN does poorly, we want to say, we are also doing poorly, but we have a white box function, and you know what is going on in the white box function potentially that is wrong, and then you can take that inspiration and go and try to correct the GNN, right? So the objective here is not to train on the data, but on the GNN's output. Any other questions? Yeah. Right. So therefore now let us sum equations to understand what is the exact problem formulation that we are trying to solve. If you don't understand that, it is okay, but let's try to stay with me. Okay. So again, what is the input? You have a graph, node, edges, attributes, class labels with every node. So every node has a particular class label from C possible class labels, and the trained GNN. Right. So this is the point I was trying to make. I don't want to make up these class labels are they are used to train the GNN, but we are not trying to use the class labels. We are going to use only the GNN's output. Okay. And what do we want to do here? Okay. So this is slightly some notation. So we want to first identify a set of B exemplars from each class. Okay. But every class I want to identify B exemplar nodes. Why B? The reason is if you have too many exemplars, it's too much load on my cognition. Right. So I want it to be a small number of exemplars. Let's say 2, 3, something like that. For every exemplar, I want to identify the signature that characterizes that particular population. Okay, which means what? That okay, this population has average transaction value beyond under a certain threshold, or they have neighbors coming from particular class label or something. I mean, GNN's predicted class label, not the true class label, right? Something of that sort. Some signature. I'll show you an example of what a signature is. And B, as I said, is to control the budget. Once I've identified the exemplars and the signature of each exemplar, then I want to now construct a Boolean function which is given a particular node V, and let's say this is the Boolean function for class I. The Boolean function for class I is an OR of the signatures of each exemplar in that particular class. Okay? So therefore, if a node satisfies the Boolean function of any of the exemplars of class I predict it to be in that particular class. And now I want to identify exemplars and the signatures such that there is exactly one function that predicts the class I and everything else is false. Right? I don't want everyone saying, oh, this you belong to my class, right? That's not useful, right? So this is exactly what we want to learn. Any question? So every class is characterized by exemplars. Every exemplar is characterized by a signature, and I want to learn signature functions such that this signature characterizes a lot of this population, and if I take the OR of the signatures of the exemplars from a particular class I, that for on a particular node, if that function is true, the node belongs to that particular class. That means if I belong to any of the exemplar group from a particular class label, I belong to that particular class label. Okay? Any question? Okay. So what are the signatures? Signatures are nothing but some Python code that are encoding some Boolean function. Okay. So what is this particular code? So for example, if you are trying to sort of do some classification, you can say that that it contains certain particular attribute information, like this is for I think which class? Rule learning, right? So this is for class 0, which is all papers with a class label called rule learning, right? So this class labels has two signatures, exemplar 1 signature and exemplar 2 signature. Exemplar 1 signature says that it has in its abstract the words ILP, meta-knowledge and hypothesis space, and in its one hop neighborhood at least 30% are belong to the same prediction label, and in its two hop neighborhood at least 20% are predict label. And this is another exemplar signature. Here it has logic program, inductive logic programming and ILP, and again similarly 30% and 20% belong to this, right? So these are the kind of signatures that we are trying to sort of learn, and this is actually something that we learn, and I will tell you how. Okay. So there are 3 steps. The 3 steps are identify the exemplars for each class. Once you identify the exemplars, identify their signatures as Boolean Python functions, and then you present this Boolean Python functions in natural language because you want it to be easily understandable by humans. What I will do here is, so in the first step, you essentially the exemplars are nodes that are located in very dense neighborhoods, right? That is what the exemplars are. I will skip this particular detail. We use something called reverse KNN, but if you don't understand reverse KNN, think about it. A good proxy is clustering. I clustered them and identify the cluster center. That's a good proxy. It doesn't work as well as reverse KNN, but it will take you somewhere over there. The details you can read up in the paper. Once I've identified the exemplars, my goal is to identify the signatures or these Python scripts. How do I do that? I use LLMs to identify identify the Python programs that fit a particular output. Okay, and then finally I use again LLMs to. This is an easy part. Once I know the signatures, I use LLMs to sort of convert that Python code into something that is easily understandable in natural language. Okay, so these are the 3 major steps, and what we'll do is we'll primarily focus on this particular middle step, right? This step is also very important, and we have some nice theory over here, but we'll go directly over here, right? So what we use here, this is not something that we design on our own. We use something called self-refine, but we adapt it for our particular purpose. This is a NewDips 2023 paper. Okay, so what we do here is that you start from here, from this particular box. This box takes a prompt, but this prompt has 4 subparts within it, right? First, it has some training nodes. The training nodes come from a training data, and it has the GNN's prediction label. And you have a certain prompt over here. I mean a sub prompt. You can within that. And there is a feedback prompt, and there is a refine prompt. There are 3 different kinds of prompts within this larger prompt. Okay. So I will go into details, time permitting, of what the structure of each one of them are. But once you give this prompt, once you ask the LLM to kind of come up with a code that fits this particular training data, it comes up with some particular code and the associated text description. So what we do next is we take this code and we apply it on a validation set, and we check what is the performance on this particular validation set. If the performance is very good, we say we'll stop our accuracy beyond a particular threshold, and this is my signature. If the performance is not very good, then we ask the LLM that, okay, these are the incorrect predictions, this is the current code that you have generated, can you try to improve this? And this thing iterates over few steps till this one of these conditions over here is satisfied. There is accuracy above a threshold, or you have crossed a particular number of iterations, right? Hopefully it will increase the accuracy and not the second condition. Questions? Any clear? Okay. So this is what we do quickly. So there are 3 prompts, sub prompts within it. The first one is a query prompt to the LLM. It defines what the task is, right? That what is the input, what is the job of the LLM, and what it needs to do. So this is kind of analogous to a loss function specification in a supervised learning, in training a neural network, right? So this is what it is doing. The second one is something that we call the feedback prompt to the LLM. What is a feedback prompt? It tells you that what is the last function that it had generated and what were the incorrect predictions and what are the correct predictions. So it is kind of telling you what are the current weights of the neural network, in the sense that you have generated this and this is where you go wrong and this is where you go correct. Okay, and then finally this is called the define prompt, which is analogous to the gradients. It tells you that when you went from pipeline like iteration I to I minus 1, what is the change that you did? And what is the change that gave you the maximum benefit? So it tells you that if you change particular threshold here from 0.5 to 0.7, that gave you the maximum benefit, right? So we give it the gradient sort of information, the marginal information that allows it to sort of do well. So with this, we just keep on iterating and we get some output. Yeah.
How did you identify that change, the gradient?
This one. So if you have this, if this goes between 0 to 1, you can just slide a window over there and you can see where you, I mean, with some particular this thing, right? I mean, granularity, right? And you can identify where it is. Okay, so results. Well, the results are, I mean, I don't have a lot of time, right? 2 minutes. Okay, but the results. The main thing that I want to point out here is that there were not too many baselines. As I said, we're the first one over here. So you can see this is our technique, GNN exemplar. We call it GNN exemplar because we're explaining GNNs with exemplars, and all the other techniques are really poor because we're not made for it. So I'm not criticizing the method. It's just that the reviewers love baselines. If you say no baselines, they will not accept the paper. So we have to compare, but we are they are not made for this, so they were not very good for this particular task. And we also did a survey after this, right? So what we did was we took up many examples and we did a survey over 60 participants, right? And they were advertised over LinkedIn, Twitter. I mean, not just people that I found, right? I mean, we did it over whatever channels that we could. And we asked, showed many examples. We had some 300 total responses about whether they prefer our explanation, which is text-based, versus just like a graph-based explanation of the two-hop neighborhoods, right? And in general, like you can see that always it is preferred over a text-based explanation, and the statistical significance test also kind of tells you that this is not by chance, but but I mean there is a fact. I mean there's something factor behind it. It's not something that's purely due to chance, right? What kind of examples? For example, I mean, we have seen some examples like rule learning, for example, right? If this is the node that I'm trying to predict, a subgraph explanation would be something like this, which is very hard to infer, like what is going on. And here we are not even showing the node attributes. If we show that, it will be completely flooded with information and you have no way to process that, even in a two-hop or one-hop neighborhood. But here we just kind of distill that it has certain number of certain keywords and certain percentage of your neighbors come from your class and some from the other class. Like what is the level of homophily you need to sort of belong to a particular class, and so on. And again, this is what the GNN has learned, not the true data, right? So yeah, and also it gives you certain diagnostic abilities, like where it is going wrong. So for example, this was a heterophilous graph, and heterophilous graph means that where two nodes can be neighbors but still not share the same label. If this happens fairly commonly, then that is called heterophilous. So we found out here is that this is a GNN which was a node I think node 1 over here, right? So the GNN's prediction says that it belongs to this particular label, but it actually does not belong to that particular label. So the GNN is using homophily to predict on a heterophilous graph, so we know exactly what it is going on, right? So quickly, so I think we have covered, like, this is the first one to sort of do this kind of stuff. But in general, if you want to read more about this, and this is going to be presented next week in NeurIPS also. This is the student. He did most of the work. I'm presenting it. Paper and code. These are all available, right? So feel free to download, use them in whatever way. But in general, this is not the end of the story. I want to sort of still highlight what are the limitations. The limitations are we're still banking on correlation and not causation, right? That let's be clear about that. So you will still want to look into the internals of the model, and therefore, what is the answer? I think mechanistic investigation of GNNs is sort of the area where we would like to sort of work towards. And if you want to work on this area, please join for a PhD, right? There are hope I'll be happy to sort of investigate more in this particular area, right? And I think that's about it. I'll be happy
So
to take
in the interest of time, we can have offline chat. We can start the next speaker now. Is it okay?
Sure, absolutely.
We thank the speaker. So the next talk is, the next talk is by Dr. Saurav Prakash. He's an assistant professor in the Department of Electrical Engineering at IIT Madras, and he is also affiliated with Center for Responsible AI. He received his BTech from IIT Kanpur in 2016, and he completed his PhD from USC. After that, he was a postdoc at IISc for a couple of years before joining IIT Madras. His interests vary from span information and coding theory, machine unlearning, federated learning, and hyperbolic geometry. And he also is an PM ANRF Early Career Fellow. So we welcome the speaker for today's last session.
Thank you. Hello. Okay. Yeah. So thank you to the CSML team for inviting me, and thank you for the kind introduction. So I guess this is the last talk for today. Okay. So I guess everyone can sit back, relax. Whatever you understand out of it, it's fine. Don't stress too much. And of course, you can ask me questions after the talk over email and so on. Okay, so as the title suggests, efficient solutions for machine learning at the edge. I'll be covering some of my recent works which try to deal with this area where you want to implement AI ML applications at the edge, but there are a lot of constraints in terms of bandwidth, computation, memory, communication, so all these things. So I will kind of present some of the interesting things that I've been doing here. Okay, so yeah. So first the motivation. So there is a lot of research and development that is going on in the emerging 6G and beyond networks. And it's not wrong to say that in all these networks we have a lot of devices, our own phones, our own laptops, and we are continuously generating a lot of data. So data, we can say, is kind of getting born at the edge, a lot of data. And due to privacy, latency, bandwidth and scalability concerns, a lot of data processing is being driven closer and closer to the edge devices. For example, we may want to unlock our phones using our face. So we cannot expect that device to connect to some server when I'm unlocking the phone. Imagine suddenly your network has issues, so you won't be able to use your phone. So that processing has to happen on your own phone. Okay. So, and then rich compute, communication, sensing and storage resources in the 6G and beyond networks, they are actually also suited for on-device AI and ML applications such as the personalized healthcare. So both we have a lot of concerns and also we have the right resources also currently. So can we combine all this to have a better ecosystem? So how to enable AI ML applications at such a massive scale is the overarching question that I try to answer in my research. And a lot of companies are also addressing one or more aspects of this question. For example, Microsoft, Google, Flower is a federated learning company, and so on. Okay, so some fundamentals. So after all these talks that we have been having, I don't think I need to motivate a lot about machine learning. but still let me just briefly describe. So we have a data set. Data set has all these features, and then each of these data points has some label. So this is just basic supervised machine learning. And then what the idea in machine learning is that I try to capture this information in the data set into some model parameters such that I can use these model parameters to make predictions later on. So at the high level, this is what machine learning is. And typically we would like to do machine learning using some form of gradient descent algorithm. So very basic stuff. So we want to minimize some loss function, there is some regularization, and then we want to do some iterative updates in order to do the machine learning. So key thing to note here is that this overall gradient which is used to update the model, that is kind of sum of the gradients corresponding to the data points in that batch of data, or if you are doing gradient descent, then it is on the entire data set and so on. So what I am trying to say is that in each model update you need certain number of data points using which you are going to update your model. Now it may happen that you have a lot of data points. So in that case you cannot compute this sum gradient in one location. And also you may want to do it very efficiently and in a fast manner. So you want to do some parallel computing. So in parallel computing, this is one scenario, very basic. So data set is partitioned into 3 parts. Each partition has a subset of data points. So what will happen in this setting is that each client, each server, each of the worker server is going to compute the partial gradient corresponding to its own data set. So what will happen? These things will happen in parallel. So hopefully overall my computation time will reduce. And then at the server side, all these gradients are combined, and then you are going to update your full global model. So this is what, in a nutshell, the distributed gradient descent is in the centralized setting. So now there is something called federated learning. I think some of you might have heard about this topic. So the idea now is that you cannot control the data placement. So data is lying at the edge devices. And then each of these clients may want to collaborate in order to learn some individual model, maybe a personalized machine learning model, or maybe they want to learn one common model, all these things. But then the data set is not in one cloud. Data set is at the edge. And there is a lot of privacy concern. So you don't want to, for example, this user will not like to share its own data set with the server. So in that scenario, how do I enable a decentralized machine learning ecosystem addressing all these privacy concerns of the user, as well as addressing the efficiency bottlenecks which arise? So at any point, if you have any question, just let me know. Okay, so I kind of work in 2 paradigms. One is this setting. You can imagine that you have some data set, and then you are the user, and then you want to do some processing with your data set, either some inference task or some machine learning task. But you want to ensure the privacy of your data as well. For example, currently if you are talking with some chatbot, let's say you are talking with ChatGPT, you are sending all your queries to the OpenAI server. Now they may say that we are not leaking your information and so on, but I don't know how much we should trust these companies. So what I'm trying to say is that ChatGPT or Gemini, all these chatbots are providing me a lot of utility. That's why I'm willing to share some of the information. But then in this process, we may be exchanging very private data sets, for example, health of ourselves, then maybe health data of our parents, our own other family members, and then maybe some personal life details. And somehow, let's say it gets leaked, then it might be a big issue, right? So you want to have some privacy of your data, but at the same time, you want to utilize the cloud resources, which is provided by big companies, for example. So how to balance this trade-off? Maintain your privacy, at the same time get a high utility. So this is one paradigm that I work in. Another one is the federated learning setting. So we have different users, and then there is some company which is trying to get some updated global model. So the way federated learning happens is that each client trains a local model on its own dataset. For example, this user is training X1T on its local dataset. And then these individually updated local models are uploaded to the federated learning server. So now what the server does, server combines these locally updated models to obtain a global model, a new iteration of the global model. And then this global model is transmitted back to the clients for the next communication round. So in a nutshell, the way federated learning works, local training at the clients, global combining of the models at the server. Repeat it many times until some convergence notion has been achieved. So yeah, so this looks very nice, but then when you try to implement this in practice, these settings in practice, you have a lot of fundamental challenges. For example, all of our devices are so heterogeneous. Even I have laptop and mobile phone. You cannot expect them to run at the same pace. And then there are so many users in the ecosystem. There is so much heterogeneity across users as well. And then some of the data sets which are there, they are very large. For example, if I want to have my own genome data, all the nucleotides information and so on, then it is like 750 megabyte. So if a hospital has to store all the genomic data of 1 million patients or 100,000 patients, then the scale becomes huge. So you cannot process it directly. So resource constraints and heterogeneity exist. And then there are there's a lot of scope for errors and malicious clients. So we keep hearing about jailbreaks where someone tries to enter some prompt in some chat GPT and then it starts giving out some very important information. So malicious clients also exist in the ecosystem. And although in the federated learning setting, I said that the data is not shared with the server, only locally trained models are shared with the server. Still, even from the model parameters, you can reconstruct the original trained images if not trained properly. So this is something called model inversion attack. Okay, so these are just some of the challenges. There are many other challenges. So then the question that I mentioned earlier gets refined to some extent: how to enable efficient, robust and trustworthy solutions for edge AI ML. Okay, so with this brief introduction, let me dive deeper into one of the research problems. So the idea here is that I want to do the federated learning, but then in this federated learning process, I want to train relatively large models. The model is such that it cannot fit some of the devices. So you cannot train that model directly into the low computational resource devices. So how to efficiently and effectively train large deep neural network over resource constrained edge devices? So this is the overarching question. And key challenges: limited memory and computation. You do not have GPU acceleration, for example, in our edge devices. And then limited bandwidth and unstable wireless communication. And also you might think, okay, some of the edge devices are there, they are not competitive enough. Let me just ignore them in order to speed up my training. So what will happen is that if you ignore some of the edge devices from training, they might be having very rich data set. For example, if you consider training a health diagnosis model and then you exclude the data sets coming from the rural areas just because they may be having bad connectivity and so on, then you are excluding a significant population from your training. So if you just exclude devices for having faster training, it's going to be unfair and it's going to have a lot of bias in your final neural network model. Okay, so you do not want to ignore the weak edge devices, but at the same time you do not want to compromise the speed and efficiency of your federated learning process. How do you do? So yeah, a lot of descriptions. So let's have some very basic illustration. So the idea here is that I'm presenting 3 different mobile phones, not the latest ones. but anyway, they convey the message. So, and here I am presenting the numbers which are the internal storage for those mobile devices. So we already see if these client devices are participating in a distributed training paradigm, there is so much heterogeneity already in terms of storage. Similar heterogeneity can happen in terms of communication, in terms of memory, and so on. So for the purpose of this talk, just imagine that there is heterogeneity in memory, and I want to train a neural network model which can just fit the largest memory phone. So this neural network is large enough such that it occupies the entire memory space during local training at this mobile phone. And then these other phones are having smaller memories. What will happen? So what happens when the model is so large, small and weak devices cannot even hold the whole model in their memory space. And this is what the situation will look like. You cannot even do the local training of this large model in these two devices because their memory sizes are very small. Okay, so now how do I do federated learning of such a large model? Okay, so just to repeat the question, the goal is to enable weak client participation in federated learning. We consider weak clients that cannot effectively train the full model on its own due to limited memory space, too weak compute power. And to utilize the distributed data in the real world, we should make all available devices participate in the training process. Okay. So how to do it? The underlying theme is to have some sort of sub-model training. We have already discussed that I cannot fit the entire model in the memory of some devices. So definitely I need to have sub-models allocated for local training. Now what is a sub-model training? At a high level I'll just describe, but before that, here is just a pictorial representation of some neural network that I plan to train. So these are the input side, these are the inputs, and then these would be the outputs. Just focus on these nodes in between. These are the actual model parameters. So these will be updated during local training. Okay. So sub-model training, the idea is to allocate subset of model parameters for updation at different clients. So this client is going to get this subset of model parameters, this client is going to get this subset, and then this client is going to get this subset. So now what I see is that I am only assigning partial models at different clients, and these models are maybe just enough to satisfy the memory constraints. So how the federated learning will happen? In the federated learning process, this client will get these parameters to update. It will treat it as a normal neural network. It will do local training, update only these parameters, and upload the updated parameters to the server. And similarly, this client is going to update these assigned model parameters, and similarly for this client. Now at the server, it is receiving updated parameters from different clients. So a simple way to combine the parameters would be this. This red parameter, the first layer, first parameter, is updated only at client 1 and client 2. So the server can simply take an average, simple average of these updated ones received from these two clients. That's it. Simple aggregation rule, simple training rule. So I have satisfied the capacity issue, like each client is only going to update some parameters, so it doesn't have to train all the model parameters. Okay, but the question then becomes how to create a good submodel. So here it's like a random creation of submodel, but then I can tell you this doesn't work well in practice. Okay.
How close is the combination of these submodels which aggregate when you do the aggregation and you get the final output? How close are the outputs compared to running the entire neural network one shot?
So this closeness is difficult to define, because you see there is no data set at the server side. So yeah, of course, if you train the entire model at one client, then these parameter, whatever you will get from this subset of parameters is going to be slightly different, and it can be very different depending on how the training happens. Yeah, but the thing is that the server doesn't have any data set, and the clients are very weak. So I have to do some sort of submodel training. Okay. So these are some prior works, and these were some prior works. And for example, here what is happening is these black parameters are not shared with the clients. Only these yellowish orange parameters are shared with the clients. So what is happening here is very simple. You take each layer of model parameters, you assign only a subset. So this client is getting this subset of parameters. So one model parameter in each layer. The next client, it gets these parameters plus some additional parameters in each layer. So you see, you are creating different groups of parameters such that the smaller group is always contained in the larger group, and it's a very heuristic thing to do. Okay, so it's just that you are increasing the subset of the parameters that is getting assigned to the clients depending on their capacity, memory or computation and so on. And then you need to have some clients where you have to train all the model parameters. So this was a method which was proposed. Surprisingly, it got accepted in 2 conferences at the same time from different groups. But anyway, they were lucky, I guess. Yeah. So I mean, there were some very minor changes, but not that much. Okay, so then you have addressed the problem of different capacity. This client has the lowest capacity, this client has slightly larger, and this client is having the largest. Huh.
So, what is the benefit of dividing the parameters in this way when we can actually train everything on the bigger systems?
Oh, so imagine that you have some clients which are offering some very rich data. So this last client doesn't have enough data points.
Just the parameters are like we are dividing them, but then the data could be.
Yes, yes, yes. And in the extreme case, maybe this client doesn't have any parameter. For example, the server has a lot of resources, it doesn't have any data set. Yeah. Okay. Okay, so this is another method. So this first method was working directly on the model parameters. The second method, it works in the SVD parameters. So what happens is that you take the weight parameters and you do some sort of decomposition. Now this decomposition is related to singular value decomposition. So what happens is that you divide it into, you decompose the weight matrix into components which are called the principal components, and these principal components, they are kind of associated with some singular values. So larger singular value, more important are those principal components. So this is where used in a lot of places for doing some approximation. For example, signal processing, when you do, you might want to have some largest singular value corresponding principal components. And yeah, so this is one idea. So you take the weight vector, you do a complete SVD, and since you have to assign lesser number of parameters, you drop the principal components when you are assigning to smaller clients, to the weaker clients. So here if you have n principal components, you are only assigning r principal components. And this r could be 1, 2, 5 depending on how many principal components can be processed at the client. So just to revise, this method was working directly on the model parameters. This method, it decomposed the parameters first and then worked on dropping the principal component. So this is kind of top principal component method. Okay. So again, you solve the capacity issue. This client had the lowest capacity, and so you have assigned it the least number of principal components, and then this client had the maximum capacity, you assigned it the most number of principal components. But then there is a fundamental issue even in this method. So one thing I can tell you is that this performs better than the previous method, but then there is a fundamental issue with this method as well. So the issue is this. So what I am showing here is normal training. So I am allowing the model to train in the federated learning manner such that all clients are training on the full model parameter space. And then what I am doing is that I am doing a I am doing the SVD of these 4 blocks of parameters in ResNet 18. and I'm trying to see how many principal components are required to approximate the weight parameters properly. So now that proper is something that we can define, but essentially can you approximate with your principal components you have selected your original weight matrix. So this is kind of connected to rank. So if you are rank 1 matrix, then it's enough to just have one principal component, but this may not hold. So what we saw that in the beginning of training, you need almost all the principal components to have a good approximation of your weight matrix. And even at the end of training, when your training has been done, still you need at least 50% of principal components to have a good approximation of your true model parameters. So now from the beginning, if the clients cannot train even 50% of model parameters, they can train only, let's say, 25%, you are going to lose a lot, because from the beginning you are assigning very small number of parameters for training. So even though you went to SVD domain, you cannot compromise on, you have to kind of update all the principal directions, at least in the beginning. So this is where this method was lacking. Okay. So low rank structure is actually gradually attained across different layers also, and a single low rank model, it incurs severe reduction in model capacity. Okay, so how to design a principled way, I mean here principle is not the principal component, but how to design a proper way of splitting and utilizing the weak clients. So this is the question. So this is our method. So before the method, so this was the paper which was accepted last year. So the method, before describing the method, that let me show what is the basis of the method. So here there are two different clients. They are training independently of each other. Random process, they may be sampling different data points and so on, but the initial model parameters are same in each of these two layers. At the end of training, what we see is that the initial layers, they have learned similar information, but at the last layer, which is closer to the output, we see that the clients have learned different knowledge. So the model parameters are kind of differing. So as you are closer to the input, you are learning similar information in different clients. As you are closer to the output, you are learning dissimilar information across clients. So you see, if you so this kind of gives rise to our method. So if a client cannot train both layers, then it's better to drop the initial layer from training somehow, because the other client will be able to train similar knowledge on its data set. And this we also demonstrate this phenomena. So this is also related to the case where you get a pre-trained neural network and you freeze the initial layers, you only update the last layers and so on. But then showing that this happens even during training is something we did. But anyway, so here there is CIFAR 10, ResNet 20, and this is an SVCCA metric. So the idea is that this metric is between 0 and 1. Higher the value, closer the parameters. So we see that in convolution 1, which is closest to the input, we have a high SVCCA. Convolution 17, it has a low SVCCA. Similarly, even in the LSTM, we see the embedding layer, which is the kind of the initial layer, it has a high SVCCA across clients, and then the LSTM layer it has a lower SVCCA. So the input side layers, they are kind of learning similar data across independent clients. Okay. So this is our method. At the weak clients, what we will do is that we will send both layers. The weak client, what it will do, it will take a forward pass through the first layer. So it has its inputs, it does a forward pass through its first layer, and then it will drop this neural network parameters. It will not change anything in the first layer. It's only going to do a normal machine learning training on its local data set through these intermediate activations, and only update these parameters in the second layer. So weaker clients are only updating the output side subset of layers. So weak clients contribute only to the output side subset of layers. Okay, and then these updated parameters are shared with the server only for this layer, second layer. And this is how two client system will work. In the strong clients you are going to update both the layers. In the weak client you are only going to update the second layer. And then these updated parameters are shared with the server. The way we did was we did a simple averaging of the parameters as received from different clients. So these parameters are received from client 1 and client 2 both. So this will be these parameters plus these parameters by 2, simple averaging. And these parameters are only updated by client 1. So I do not have anything to average with. So I will just copy paste the values in my updated model. Yes.
After some communication round, the weak plate should be a strong plate.
Weak line should be?
Strong plate.
Oh, why?
Sometimes after some communication round, weak plate may be a strong plate. That time, how can you apply that?
So you, yeah, I mean you can. So if it's really that type of dynamic, you can simply assign it a larger number of output side subset of layers. If it becomes very strong, you can just assign it all the layers. See, in every round you have a control, right? You, like what parameters you have to assign, that has to be decided in every round. So if in a certain round you see that the client capacity has increased, maybe availability has increased, its memory has become free. At night when we are sleeping, the phone is kind of idle. So in those cases, yes, you can assign it a larger number of parameters for updation. Sure.
No. You mean that time stronger plate, that time we will update both Y and
Yeah.
When it is still strong, that time we will update both.
Yeah, it can. Yeah. This is an iterative process. Many rounds are happening. If it, at the beginning of each round, you can ask the clients how many parameters they can train, and you can assign from the output side. That's it. Sure. Okay, so some experimental results. I mean more of simulations. So removed. So this is ResNet 20 CIFAR 10, and we just hand coded what is strong, what is moderate, what is weak. So I'm only going to present with strong and weak clients. So let me just focus on those. Strong clients are the ones where I'm assigning all the model parameters. Weak clients are the ones where I'm assigning only these last few blocks of parameters. Fine. So does this help? So these are the experimental results. So let me describe it. Each row is representing a federated learning setting. The first row you have only strong clients, 16 strong clients. So everyone will train with a full neural network. In the next row I have 16 strong clients, and then I have 16 more clients, but they are all weak clients. And then similarly in the third row I have 16 strong, 32 weak. So what is happening as I am adding more and more weak clients, I am getting more and more data exposure also for the global model. So I should be kind of getting better and better performance. So with the some prior method, if we directly apply it, there was no baseline to begin with, but if we apply that method, so from 60% it's only improving to, let's say, 65% for this case where you are having 16 strong and 112 weak. But for our method, we improve significantly from 60% to 77%. So this is kind of showing that embracing FL is our method. It is better utilizing the weak clients which are joining the federated learning training process. So this is our key contribution. If you have weak clients in the ecosystem, can I incorporate them better? Of course, one is for fairness for those weak clients and also for the global model performance. 5 minutes? 40 minutes was the time?
8 minutes.
8 minutes. Okay. So let me just mention one more problem. So federated learning of large models at the edge is embracing FL enough. So what happens, one common issue with all the methods, including our method, is that they require at least one client to train the full-sized model. But then it may happen none of these clients can train the full model. So all clients are weak. Then how do I do? So this is what we developed in another work. In the interest of time, let me skip all the details, but let me just show you the final results. So this is one case. Let me go to this one. So I have non-ID federated setting. This is the case where all clients are training with full-size models, and then this is where only 80% model parameters are utilized for local training in each of the clients. And this is the setting where only 20% of the model parameters are used in every client. So we can see that our method Prism, it retains the performance by significant margins. So in the full model case, it is around 85%, and in the scenario where it is extremely resource constrained, where every client is only updating 20% of model parameters, our performance is still above 80%, while other methods have gone below 70%. So we are really able to beat in other methods in this resource constraint scenario. Okay, so I'll just mention two more things in terms of research. So I also work in machine learning. So the idea is that there is data leakage which can happen through models. For example, you might provide some prompt and then it starts giving out the original training data set. So this is also something which is very important in today's times. So I kind of work in this area as well. And then there is something called hyperbolic machine learning. So the idea in hyperbolic machine learning is that you have a lot of data sets which are hierarchical in nature. For example, genomic data sets, then generation phylogenetic trees. For example, this is a cancer phylogenetic tree. So we can see that the development of mutations is following some hierarchy. So in such large hierarchical data sets, hyperbolic machine learning, it helps significantly. So I work at the intersection of hierarchical, large, as well as federated learning setting. Okay, so how to do federated learning with high dimensional hierarchical data. So this is another area I just wanted to mention. And let me just do some philosophical discussions. So yeah, what a lot of time is there. Okay. So yeah, since so many undergrads are here, I thought I'd include this in the slides. So I guess so many talks you all have attended, so you can already see so many interesting things going on. So hopefully these would not add a lot of value, but still let's try. Let me try to do something. So we all know this symbol ChatGPT and the original ChatGPT model GPT 3.5, and then these were decoder models, and then underlying these decoder models, I mean these are kind of transformer models. At the core of transformer models is the self-attention mechanism. So why I'm having this type of image in my slides, all I'm trying to show is that all of us are familiar with ChatGPT, but I don't know if we go back and ask people around us, how many of them will be familiar with what is self-attention. So there are a lot of technologies around us. It's very important to develop those technologies, but a lot of research and development has gone into developing simply these transformers also. LSTM, bi-LSTM, this and that, and then you arrived at self-attention and transformers. So it's not that suddenly these technologies came out in the market and suddenly the research and academia is of no use. So it doesn't work like this. So and all I'm trying to say, the technologies you see around you, which you appreciate a lot of research and development has gone into those. That's why you need to do research, to develop technologies which change the society. And then this is one illustration of that core self-attention component. This person, JLMR, is very good. You can go and see his websites and books and so on. All I'm trying to show here is that there is a lot of matrix operations involved in self-attention. So I'm not trying to tell you what this is. All I'm trying to tell you is that a lot of matrix multiplications are involved here. So all that is happening is a lot of linear algebra and a lot of intuition. These were kind of the key ingredients. And this is what happens in a lot of these problems. You boil it down to at such an extent that you just have to work on the fundamentals. In my case, fundamentals are like linear algebra, probability, some optimization, some programming also, but that's it. And you should bring a lot of intuition. And typically, I would believe this would happen in a lot of other research directions as well. And then just to drive the point further, So attention is all you need. This was the paper which proposed the transformer architecture and self-attention. So many people were involved. So many people from Google, so many people from University of Toronto, and so on. Now why I'm having this? So except one person, he's a star, Noam Shazi, but except him, everyone was either an MS graduate or a PhD graduate. So many minds for many months, were involved in developing just one transformer architecture. So you can imagine the importance of doing research. So research and graduate programs, MS, PhD, they kind of give you enough time, and with guidance of under the right mentors, you are able to train yourself so that you can contribute to such technologies, either during your own graduate programs if you are lucky, or maybe down the line when you join some company, some academia, something. Okay, and then further, for some reason I kept hearing when I was preparing slides that there is not enough opportunity in India, but that's not the case. All these people are based in India. They have their PhD. So, and these are just some companies I found, went online, checked their research pages, and these are all the people listed there. You can go and check. Maybe some have moved between companies, but by and large they are in India. Okay, and then Indian government is also pushing a lot of initiatives. You might be able to hop onto one of these and become the leader in that field. So this is also something you should look into. And then since I'm from IIT Madras, I need to do some advertising. So I do research at IIT Madras. It's a very beautiful campus, and yeah, we have been NIRF rank 1 in the overall engineering and all these rankings, but I think in ranking and all is not that much you should focus on. There are a lot of good institutes, including IISc. And then, but one thing I really like about IIT Madras is the research park. So it is the first Indian academic institution with a research park. And the research park is very well working. It's fully functional and it helps a lot in a lot of collaboration. And it's right outside IIT Madras. So much of innovation and patents are coming out. And some very recent examples from incubation to Dalal Street. You might have heard about this IPO that came out of Research Park, Aether Energy, electric bikes. And then Agnikul has also been raising a lot of grants one after another. So these are just some. So we have very deep tech startups going on in Research Park. And why do research in the E department from where I come from? So we have one of the largest departments in the IIT Madras, and so much keeps coming out of our department. And we have many different domains. You can go and check out communication signal processing. I come from there. And then you have control optimization, microelectronics. So anything you can imagine related to electronics, power, everything, signal processing, will have it in our department, including me, AIML. One more minute. Yeah. And then some placement data. So MTech, you can check these data online. So MTech placement salary, average CTC salary 30 lakh, PhD 32 lakh. But then these numbers do not reflect what people do when they go for higher studies. These are just the placement data for that batch. Okay, and then opportunity for students, PhD, part-time, external PhD. This is something where you can work in industry and also pursue research at IIT Madras. Of course, master's is there, then project staff positions are there. So if you do a project position and you stay in the project for 6 months, you do not need to give GATE exam in order to qualify for interview. So this is something you should look into. So you don't need to give GATE and then come to interview. You can do a project, you get to know the advisor, and then you can just join for MS PhD. Yeah, that's it.
Okay. And then both the speakers are here. So now, since everything is open, you can contact anybody for questions. So we officially wind up today's session. Okay. And then thank you so much for all the speakers and attendees for taking